In this video, we're going to introduce and describe the pumping lemma for regular languages. There's also a pumping lemma for context-free languages, which is a bit more complex and we'll talk about in a different video. But for now, we're going to show what the pumping lemma is. The pumping lemma tells us something about all regular languages, and we're going to see how we can use the pumping lemma to prove that some languages are not regular. And then finally, we'll see an example proof showing how we can prove, using the pumping lemma, that a language is not regular. Let's begin with a couple of example languages that are not regular languages. The first one is probably the most important one, and one that you should really be familiar with. We have a bunch of zeros followed by a bunch of ones, and the number of zeros is equal to the number of ones. And the reason this is not regular, the intuitive reason that this is not regular, is that it requires counting. In order to check whether this string is in this language or not, you have to count up the number of zeros and then check to make sure that the number of ones is the same. And this ability to count or remember things, remember arbitrary amounts of information, is just beyond the capability of regular languages and finite state machines. So this is the prototypical example of a language that is context-free but that is not regular. Let's look at another language. Every string composed of zeros and ones, where the number of zeros is equal to the number of ones. They can be in any order this time. This is a similar language, and it's also non-regular. Like the language B, it requires you to count up the number of zeros and count up the number of ones, or perhaps keep track of the difference in the number as you go through the string. And as this number, this difference between the number of zeros and the number of ones, can be arbitrarily large, it's beyond the capability of a finite state machine. A finite state machine has only a small number of states, a finite number of states, and so it only has a limited amount of memory, and it can't hold arbitrary numbers in that memory. And so these two languages are not regular. Let's look at another language, D. Here it's strings of zeros and ones, and W has an equal number of O1s and 1-0 pairs. And this would appear to be very similar to the previous string and also appear to require counting. But surprisingly, this is a regular language, and I'll leave you to think about why it's a regular language. Because in this video we want to focus on proving that languages are not regular. So how can we prove that a language is not regular? Well, we're going to introduce a key concept, a key technique in this video called the pumping lemma. And there are two versions of the pumping lemma. One is for regular languages, and one is for context-free languages, which we'll look at in later videos. What we're concerned with here is the pumping lemma for regular languages. So just be aware that there's another pumping lemma for context-free languages. This one's a bit simpler and probably the best place to start. And in a later video, we'll get to the other pumping lemma. First of all, any language that has only a finite number of strings is regular. So we're really only concerned with languages that have an infinite number of strings, which means that some of the strings are really long. You know, obviously if you have an infinite number of strings with a finite alphabet, they have to get longer and longer and longer. So try to imagine a finite state machine that generates really long strings. Every finite state machine has a finite number of states, so let's consider the finite state machine that generates these long strings. Well, it's got a number of states, a small number of states. In this example, the number of states is 5. Okay, I'm not showing the actual transitions because I don't care exactly what the transitions are. But the point is that with only 5 states, you've got to be able to generate really long strings with like 20, 30 symbols from the alphabet. And the only way, how can we generate a long string? Well, the only way we can do that is to take a cyclic path. And now the question is, how long can the string be without containing a cycle? Okay, so let's look at this. We've got 5 states, and we have to get from the initial state to one of the final states. And so in this case, it could be, let's see, 1, 2, 3, 4 symbols long. At this point, you know, can we do 5 symbols? Can we do a string with 5 symbols without a cycle? Let's see, 1, 2, 3. And in order to have 5, we've got to go someplace else before we hit the final state, which means we've got to go back to someplace we've already visited. So with only 5 states, we can generate strings up to length 4 without having a cycle. So how long can the string be without containing a cycle? It has to be less than the number of states. N is the number of states. Any string of length 5 or longer must involve a cycle in the finite state machine. Here's the key idea behind the pumping lemma. If you can go around the cycle once in the finite state machine, then you can go around it 2 times. And that string must also be in the language. In fact, you can go around the cycle lots and lots of times. So you can also go around the cycle I times. And we should also note that there's another case. You can also skip the cycle altogether. And that string must also be in the language. So another way to say this is we can go around the cycle 0 times. So I can be 0, 1, or something larger. We can go around the cycle multiple times. Let's look at a finite state machine that contains a cycle. And here's an example of a machine that contains a cycle. There may be other edges in here, but I'm only concerned with a path from the initial state to the final state that goes around a cycle. And in order for there to be a cycle, then necessarily there must be some state that gets visited twice on the path. So I've just labeled it Q9 so we can talk about it. So there's at least one node like Q9 that is visited more than once. So as we go around this path, we go to the X part, the Y part, and then we visit Q9 a second time. Finally, we end with the Z part, and we get to the final state. So the key thing with a cycle is there's at least one node that is visited twice. And so we can divide, if we identify one such node, we can divide any string that's generated that involves that cycle as consisting of 3 different parts: the X part, the Y part, and the Z part. So if this is our node, the Y part consists of the part of the path that goes from Q9 to Q9. X goes up to Q9, and Z goes from Q9 to the final state. So our string is really composed of 3 parts. And the thing to notice here is that all strings of the form X, Y to the I, Z, are in the language for any I greater than or equal to 0. So the string XZ, in other words, where there is no Y, where the I is 0, is in the language. And we might go around the cycle twice, so X, Y, Y, Z would be in the language too. So that's an I of 2. So all strings of this form are in the language. So let's try to say this a little bit more carefully. What can we say must be true of a regular language? If A is a regular language and A contains a string S that is sufficiently long enough, in other words, if the language is regular and it contains a string S that's long enough, then S can be divided up into 3 parts, X, Y, and Z, such that X, Y to the I, Z is also in the language for every I greater than or equal to 0. Now, sufficiently long enough, what exactly does that mean? That means if A contains a string that's longer than, as long as or longer than some length, and we'll just call it P, which stands for the pumping length, then there must be cycles in the finite state machine that describes that language. So if A is a regular language, then there is some length for that language such that any string that's longer than that or as long as that, in other words, for a string S whose length is greater than or equal to P, then that string has to be divisible into 3 parts, x, y, and z. And furthermore, the language has to contain x, y to the I, z as well, for all I. Now notice that this P is a function of the language, not of the specific finite state machine. Okay? Now it may be that you can create a finite state machine that would accept string S without going around a cycle for the language. But the point is that every language, if it's regular, it has this pumping length, P. So one way to think about this might be to imagine that, okay, I've got a regular language. Let's look at the minimum finite state machine. And from that we can find out a P. Okay? So for every regular language, there is a finite state machine that describes it. And you can just choose one and say that, well, if this one describes the language, then that finite state machine has a P that has this property. Now there may be other machines that don't have a cycle for strings of that length, but the point is that first machine describes the language, and any string that goes around a cycle in that machine has to be in the language as well. So you can just imagine looking at the finite state machine with the fewest number of states and deriving your P from that. But the point is, we won't ever derive the P. We just know that for every regular language, there is some length, there is a pumping length, such that any finite state machine that describes it has to contain cycles, and therefore x, y to the I, z is in the language. We can also make a couple other statements about this. The length of the y part has to be greater than 0. Otherwise, this would be pretty much a vacuous statement. It would have no meaning. If y is the empty string, then it wouldn't make much sense. In order for the cycle to really be a cycle, it has to have at least one edge in it. Okay, so you have to actually have an edge there. And perhaps there are no other nodes in the cycle, but there has to be at least one edge from Q9 back to Q9. And the other thing is that the length of x and y combined has to be less than or equal to p. In other words, you have to hit the cycle, you have to encounter the cycle before you go through too many symbols. In other words, before you go through p symbols, you have to actually encounter the cycle. Okay? So we know these things are true for every language that's regular. If the language is regular, there is a length p. We may not know what it is, okay, but there is a p that exists. Let's try and think about some special cases of this loop. Okay, here is another example, and here again we have a cycle, but we have not just one node that's repeated, but several nodes that are repeated. Okay, in addition to Q9, these other two nodes are also in the cycle, and so you can see that we can still break the string into parts x, which is up to one of these Q9 nodes, then y, which is around the cycle to Q9, and then z. And so here you can see that the y and the z might overlap. It might be the same edge that we're taking, but that's okay. And likewise, if it had gone the other direction, there might be some overlap between the y's and the x's. So that's one case. Here's another case where the z part is actually empty. And here we are going straight through, encountering 1, 2, 3, 4, 5 nodes, all 5 nodes in x. And then at the very end we have a cycle, and it's sort of the minimum size cycle. So in this case, the length of y is greater than 0, but it's just barely greater than 0. Also, in this case, our pumping length is apparently 5, and we're hitting it right at the sort of the very last minute, if you will. But we are still hitting it. Now, I want to emphasize this. If the language is regular, then there must be a length, which we'll call the pumping length, such that all strings longer than p can be pumped. And the part I want to emphasize is that the pumping length is a property of the language itself, and not a property of any specific finite state machine. If the language is regular, then there has to be a finite state machine to recognize it, so you could choose any one. And if it makes you feel better, you could choose the minimal finite state machine, the one with the fewest states. But the point is that the pumping length is a property of the language itself, and not of any particular finite state machine that describes the language. But the reason the pumping length exists is because any finite state machine that describes the language has to have cycles in it in order to be able to generate strings of arbitrary length. So there has to be a pumping length. The language has to be pumpable, we might say. Before we show how to use the pumping lemma to prove that a language is not regular, let's restate the pumping lemma one more time and state it precisely. If a language A is a regular language, then that language has a pumping length p, such that any string, we'll call it S, that's as long or longer than the pumping length, in other words, any string that's sufficiently long that's in the language, can be divided into 3 parts or 3 pieces, which we'll call X, Y, or Z, X, Y, and Z. So any string that's in the language that's longer than P or as long as P can be divided into 3 pieces. Somehow it can be divided. There may only be one way, or there may be several ways, but there's at least one way to divide the string into 3 pieces such that all these 3 conditions hold. The most important condition is that X, Y to the I, Z is in the language for every I, not just I equal 1, but I equal 0 as well, and I equal 2, and I equal 3, and so on. So we can repeat the Y part. Okay? There is a way to break the string into pieces. There may only be one way to break it up, but there is at least one way to break it up in such a way that the part in the center between the X and the Z can be pumped. It can be repeated. And furthermore, there has to actually be some symbols in the Y part. The length of Y cannot be 0. And we have to reach the pumpable part, the Y part, before going beyond P symbols. So the length of the first part of the string that includes the Y part, X and Y, has to be less than or equal to the pumping length P. So now we know it's true of regular languages. We know that regular languages can be pumped according to these rules. So now let's show how we can use this pumping lemma to prove that a language is not regular. So let's look at a language A and show how we're going to prove that A is not regular. This is the general form of the proof. And then we'll look at a particular example where we prove some specific language is not regular. So it's a proof by contradiction. We assume A is regular, and then we come to a contradiction, and we conclude that A is not regular. Well, if we assume it's regular, then A must have a pumping length. We don't know what that length is, but we assume it has to exist, so we can refer to it symbolically as P. All strings longer than this length can be pumped. Okay, all strings that are not shorter than P can be pumped. So what we do is we find a string that we know to be in the language. Okay, so we make sure that the length of the string is greater than or equal to P, and it can be any string, but but we find a string that's in the language whose length is longer than p. And then we divide it into 3 parts. And we show that the string formed from x, y to the I, z is not in A for at least one I, for some I. But we have to consider all the ways that S, the string, can be divided into 3 parts. Because maybe we didn't divide it the right way. So we have to consider all possible ways that the string can be divided into 3 parts, x, y, and z. And then we show that regardless of how we divide the string into x, y, z, none of these can satisfy all 3 of the pumping conditions at the same time. In other words, we show that this string S cannot be pumped. Okay? In other words, there's no way to break it into 3 parts so that x, y to the I, z is also in the language for every I. Okay? So we have to show that S cannot be pumped. And if we do that, then we have a contradiction, because we know that if A is regular, then it can be pumped, and every string that is at least as long as P can be broken up into the XYZ parts and pumped. So we have to show that no matter how we break S into XYZ, all the ways we break S into XYZ, that none of these can satisfy all 3 of the pumping conditions at the same time. And then we reach our contradiction and conclude that the language is not regular. So let's look at an example language and prove that it is not regular using the pumping lemma. We'll call the language B here, just for variety, and not call it A. But this is our language 0 to the n, 1 to the n, which we've already said is not regular. Now we're going to prove that it's not regular. It is in fact context-free, so this will show that we have a language that is context-free but is not regular, so we can later on show that the set of context-free languages is strictly larger than the set of regular languages. But in any case, this is our language. So here goes the proof. First step is we assume that this language is regular. Okay? If B is regular, then B must have a pumping length. So we'll let this variable P, or this symbol P, denote the pumping length. We don't necessarily know what it is, but we assume that it must exist. Now we need to find at least one string. We only have to find one string and show that that string cannot be pumped. So the string that we're going to use is this string of P zeros followed by P ones. So 0 to the P, 1 to the P. Whatever the pumping length is for this language, it must exist if it's regular. And so we create a string of P zeros followed by P ones. And now we're going to prove, we're going to find the contradiction. We have to divide S into pieces, X, Y, and Z. And we have to divide X into pieces. We have to consider all the possible ways we could divide S into these 3 pieces. Okay? And so if you stop and think about it, we're going to divide this string into 3 parts. And we can look at some different cases of where the Y falls. The Y could be all zeros. Okay, in other words, it could be over here on the left end, or it could be in the middle and have some zeros followed by some ones, or maybe it could have all ones. So those are the only ways we can break S into 3 pieces, X, Y, and Z. In this case, we're kind of sort of arbitrarily assuming that our pumping length is 7, so the string we're creating is 7 zeros followed by 7 ones. But we don't know what the pumping length is. But still, regardless of whatever it might actually be, there's still 3 ways to divide this string into XYZ into 3 pieces. And in the first case, the Y is all zeros. And in the second case, the Y contains some zeros followed by some ones. And in the third case, the Y consists of only ones. We have to show that regardless of how we break up the string S into 3 pieces, X, Y, Z, it cannot be pumped. So there are 3 cases to consider corresponding to the three cases, three ways of breaking S into XYZ. So let's consider these. Well, these three cases are that first, that Y contains only zeros. Well, I've got them renumbered here. One case is that Y consists of zeros followed by ones, and the last case is that Y is only ones. So let's look at the first case first, and we'll just ignore this for a second. So if we break the string into X, Y, and Z in such a way that the Y part contains only zeros, we know that it ought to be pumpable if this language is regular. So X, Y to the I Z must be in the language for every possible number I. And in particular, we can just double it. Y is not the empty string, so there's at least one zero in it. So by doubling it, you're going to increase the number of zeros. And in this case, there were 3 zeros in it, so we doubled it. And now we've got 1, 2, 3, 4, 5, 6, 7, 8 zeros and only 5 ones. Okay, so you can see how this is not going to be in the language because the number of zeros will increase. Okay, likewise for the case where Y contains only ones. Again, it can't be pumped because if we increase the value of I any at all, say for example we double it to 2, then it's going to increase the number of ones. The length of Y cannot be 0, so we have to have at least one in Y. So the number of ones will increase with no corresponding increase in the number of zeros. So that string is obviously not in this language either because the number of ones is no longer equal to the number of zeros. And in the last case, we have a Y that contains both at least one zero and at least one one. So it has one or more zeros followed by one or more ones. And in that case, we pump the Y, again doubling it for example. We may have the correct number of zeros and ones, but they're no longer in the correct order. Okay, we have 1, 2, 3, 4, 5, 6, 7 zeros, 1, 2, 3, 4, 5, 6, 7 zeros, but it's no longer the form a bunch of zeros followed by a bunch of ones. So this string is not in the language either. So we've shown that no matter how we break it into X, Y, and Z, it cannot be pumped. So therefore this language is not regular. Now I also want to mention one other thing. There was another condition, which is that the length of X and Y is less than or equal to P. So our string is 0 to the P, 1 to the P. And so we're saying that X followed by Y has to end before we have more than P characters. So really, the way I've broken it up, I've ignored condition 3, and we can rule out cases 2 and 3 because they violate what I called condition 3, that you have to encounter the cycle before P characters have passed. So we can rule out these cases as not being pumpable. Not only do they fail to meet this condition, they also fail to meet this condition down here as well. And so we could rule cases 2 and 3 out that way as well. Let's look at one more example of a language and show that it is not regular. In this case, our language, which we'll call F, consists of strings of zeros and ones. So W consists of a bunch of zeros and ones. And the strings in the language consist of two parts that are identical to each other, W, W. So a bunch of zeros and ones followed by the same string of zeros and ones. And intuitively, the reason this thing is not regular is because in order to check whether a string is in this language, we need to scan a bunch of stuff, an arbitrary amount of stuff, and then remember what we've seen so that we can check to make sure that the second half is equal to that. So this requires memory, an arbitrary amount of memory, which our regular languages don't have and our finite state machines can't have. So now we want to prove that F is not a regular language. So again, we're going to follow the same exact pattern. We're going to assume it is regular. And therefore, if it is regular, it must have a pumping length. And so we'll let P symbolize that pumping length. And now let's come up with this string. And in finding these proofs, the creative part, I guess, is coming up with a string that is going to work, as well as going through the mechanics of making sure you check all cases. So here we have a string of P zeros followed by 1, followed by P zeros, followed by a single 1. Clearly the first half, up to just after that 1, is equal to the second half. Now we're going to split S into 3 pieces, X, Y, and Z, but this time we're going to pay attention to our conditions 2 and 3. And that'll make our life a little bit easier. We have to have at least one character in Y, but more importantly, condition 3 says that we have to get to the end of Y by the first P characters. So notice that because we have P zeros, that means we have to, Y has to end before this dotted line right here. It cannot include the 1. So in this example, we're just kind of arbitrarily guessing that P might be 7. P might be 7. The pumping length is 7. So we have 7 zeros followed by 1, followed by 7 zeros followed by 1. And here, the length of X and Y combined has to be 7 or less. So X is 2 plus 4 more is 6. So it can't go beyond, Y cannot extend beyond the dashed line. So more importantly, Y must be all zeros. So when we increase or try to pump it, for example, by doubling Y, increasing it to X, Y to the 2, Z, what we get is a string that now has more zeros in front of this one than it has zeros in front of this one. So clearly, that pumped string is not going to be in the language. And so we've reached a contradiction and concluded that F is not regular. So these are two examples of the pumping lemma. And again, this is the pumping lemma for regular expressions and for regular languages. And later on, when we talk about context-free languages, we'll see that there's a similar pumping lemma for context-free languages. It's a bit more complex, but the way we apply the logic will be more or less the same. We assume that the language is regular, or in that case context-free, and then we know that it must be pumpable, and then we reach a contradiction and end up concluding that the language is not regular, or in the case of context-free languages, not context-free.